So, okay, let's start. Continue from yesterday. So today we are going to continue with the Python lecture. I will also hopefully go into array computing with NumPy, but we'll start with Python today. So last lecture I talked about the dictionaries and tuples. Lists and tuples. And today we're going to look at the dictionaries. And I said before, dictionaries is similar to the list. The only thing is that you create them using curly brackets, this kind of strange characters here, which indicates that this is a dictionary instead of a list. And the thing with dictionaries is that you store, instead of storing values with indexes, you store them with key value pairs. So you have everything you put into a dictionary is always a key and a value. For example, here, in this case here, I have a dictionary. I manually add things to it. So you can see you have a key here, and then a colon, and a value, and then comma, and the next pair, key, value, comma, key, value. So it's like a phone book that you can look up things. Instead of using the index, you use the key to retrieve data. So if you run this, if you print it out, you will get it like this. So, and the special thing here is that compared to lists, instead of putting 0, 1, 2, 3 in the brackets when you access them, you put the key in here. And the key can be any data type. So you can have integers, floating points, anything can be a key in a dictionary. So the square brackets are still used to access items, just like with the lists, and also the tuples. And you can see here that you get back the values. David here was 1, 2, 3, 4, 5, 1, 4, 5. And you can see you can access them using the key instead. You can add values to the dictionary by doing basically the same thing as in the list. You can have, instead of an index, you put in the key, and then you assign a value here. So now I add a key value pair like this. Now you can see we have Peter here as well, and the value that you have added here. And the nice thing with dictionaries is that you can do really quick searches of indexes of dictionaries. So in this case, you have 3 items here in the dictionary, and I can use the in operator. We used that before in when we use strings. So here I can check if it's paper in the dictionary. That will return true if it's in the dictionary, but this should return false, as we don't have a bus in our index. And these operations are really, really fast because the dictionaries are stored as trees in memory. So you can really quickly search large number of data to quickly find if it's in the dictionary or not. Had you stored this in a list, you have to kind of loop over every item in the list to check. With a dictionary, you can really quickly find out if an item is in the dictionary or not. The nice thing here is that you use it basically the same way as you use the list. So you can use the len function that we read about yesterday. You put the dictionary in here, you get the number of items in the dictionary. So that is, you can see that there are certain functions in Python that are generic that you can use for many types of data types. Yeah, as I said before, adding is the same thing here. You just continue assigning items to the dictionary. Also, same thing as for list. You can combine data types in a nested way. So in this case here, I have a configuration dictionary. I have top level keys here, general. Then I have another dictionary inside here with I have a key here, and this is a dictionary here containing the keys username and temp path. I have another key here, constant, that contains another dictionary here with floating point values. And here I have items with key, and then a value that is a list in itself. So you can have this kind of nested structures really easily, and you can access them with like this. So you can go in here, general, username, that will go general username, return Ulla in this case. Constants pi, again, constants pi, I should return a floating point value. Items values returns this list. So if we run this, you can see here that should return the second position here, which is 2. You can do this at home. There's some training assignments here. So I continue here. Loops and conditional statements. So we have gone through the basic data types of Python, but now we need to work with them in different ways. And one of the ways you work in code is that you repeat things a certain number of times, do loops, and you also you have to check if something is fulfilled or not. So the conditional statements. So we go back to this, how code is defined in Python. So every statements in Python can be grouped in code blocks. And code blocks are always started with the colon character. So anywhere we have a colon, you know in Python, the next line will be indented. Otherwise, it's not part of the code block. So in this case, the code block is print here, because it's indented here, and it starts with a colon here. This print statement is not part of the code block. You can see it's indented here. And you can have multiple statements in a code block, but they need to have the same indentation. So if you have an editor, try to set the editor to have consistent indentation. I'm in the school that you should have spaces for indentation. So I have my editor set for 4 spaces for indentation. And make sure that you always have 4 or the same indentation level everywhere. So you can see here, 1, 2, 3, 4 spaces here. And you can see here, if you run this, you get 1, 2, 3, 4. And then this is not part of the code block. And as I showed you yesterday, if I add this to this code block here, you can see here that now this statement is, this print statement is also part of the code block. But if you start doing like this, Python doesn't like it at all. So it says indentation error, unexpected indent. So you get errors. If you don't do the indentation correctly, you will get in trouble. So make sure that you have consistent indentation. So you've already seen the basic loop construct in Python, the for statement. So for, and then you have a loop variable, and then you define the range you want to loop over. So you have for I, that is the variable that changes. Range is the sequence that you want to loop over. So in this case, if it says range 10, the sequence will be 0 to 9. So this will be 0 to 9. Then you can have a starting sequence variable. So you want to start at a certain number. So there's a 5. And then this one is up until but not including this value here. So this will be a sequence from 5 to 10. And then the final parameter in the range specified here is the step. So you can step over. In this case, I do step by 3. And gives a 5 plus 3 is 8, and so on. So this statement here, it's good if you want to have the value and use that variable to reference some other data structure. You want to have the I. But in many cases, you just want to loop over a certain number of items in the list. And you're not interested in having a loop variable with a number. You just want to have the value of that position in the list. And that is actually very easy to do as well. You just have a list here. For value in values. Value will be, the first iteration of the loop, the value will be 1. And then next iteration will be 3. really easy way of iterating through a list. And the value will, of course, you have to be careful if this is a string, so that you don't do any math functions on the string, but still you get the value from the list every iteration. You don't have to access the value using a variable. But you can do that as well. So in this case here, I have two lists with the same length, one with a string, one with integers in them. And then we have for I in range len a. So this is a very easy way to create a list or create a loop that is loops over the entire length of a list. So len will return you the number of items, in this case 5. Range will go from 0 to 4. So this is the default way of doing that. And then you use the variables here, I here, to access the elements in these two lists to do an operation. So sometimes it's a good idea to have this loop variable. But there is another way of doing it. If you want to have both the value and I as a loop variable, you can use the enumerate function in the loop. So in this case, it's extremely annoying. You have a list here, and then I here will be the current loop index. So it starts from 0 going to 5, and value will be the value of the list. Now you can easily do print I, value, but you don't have to reference the list itself because you get the value every iteration. And you can actually, sometimes you can visualize how it looks like this here. So you can see actually what it is here. Enumerate actually creates a data structure where you have pairs of values like this. If you print out this one here, you don't see any. It's an efficient. So this is just to visualize. You convert it to a list, and then you get this one here. Otherwise, it's actually it doesn't print out. It's an object to make it fast to do this operation here. You can also do iterate over multiple lists at the same time, and then you can use the zip function. And you will actually, in your CalFirm code, you will see many examples where we loop over multiple structures at the same time and use zip to get out the current element coordinates, the current topology for that element, and we use zip for that. In this case here we have xpos and ypos, so let's see our coordinates, and then we have we want to just print out every coordinate separately here. And then we combine these two together and assign them to x and y. And you can see it does the same thing as the enumerate, basically. If we do this zip, you can see here that it combines the two values from the list into a new list here that we loop over. So every time we loop here x and y, we assign this pair here of values. And then, of course, you can have lists, nested lists. So that is, you have lists inside lists. And if you want to loop over every value in a nested list, you start with outer. So in this case, we have coordinates here, for example. We have coordinates of 50, 50, 130, 70, and so on. And we can see those as points. So we loop over P, which is the coordinate point, in points. And P itself will be a list. So we can do for chord in P and print chord. So now we will get just a dump of all the coordinates in our list here. So 50, 50, you can see it loops over this one, and then it takes the next list and it iterates over that. And you can see here that the indentation is important here. So the outer loop here, the code block for the outer block here is this here. So the inner loop is executed for every outer loop. And it itself has an inner code block with a print statement. So indentation is important. So what if I have a dictionary instead I want to iterate over? Then there are multiple ways of doing that. One easy way is to use the items method of a dictionary. That returns you a key and a value for every iteration. So you can print out the key and value. The same thing here if you want to print and look at how that structure looks like. You can see here that the dict items here contains this pairs here. It converts it to a list of pairs. You can also, if you're not interested in having both values at the same, you're just interested in the key, you can do for key in name dict keys. So this method here returns a list of the keys in the dictionary, and then you can loop over them, and then you can use the key to access the value in the dictionary itself. Like that. And of course, if you're only interested in the values of the dictionary, you don't care about the keys, you can use for value in name dict values. Then you get only the values. Also note that when you iterate over a dictionary, it's not necessarily going through in a certain order. It depends on how they are stored in the tree. So it could be that you iterate in a different order than they are added to the dictionary. There's another way of iterating. If you are iterating in a more algorithm sense, in numerical analysis, for example, you want to iterate using a condition. So while a certain condition is fulfilled, continue doing this iteration here. So here we have a while statement, and a certain criteria here determines if this code block is going to be executed. So I set up the iteration here, then I loop over this, and it will continue iterating until this is false. So you can see here sometimes it stops. So this is more if you want to continue computing and iterate until a certain criteria is done, and then you can use this. Same structure here, while colon here for a code block. This is the condition, and then it executes that block every time until it's false. Then you also have normal conditional statements. So like if certain value is true, then execute something. So in this case here, if I equals to 0, execute this one here. And equality in Python is 2 equal signs. You have to be careful here. If you do I equals to 0, that is actually an assignment. So if you want to compare something, you have 2 equal signs. So if you run this, it will print out this. If it's not 0, it will not do anything. Then you can also have a else statement here. So you have if, and then it will if this is true, it will execute this code block. Otherwise, it will execute this code block. But the same thing is true again, that you need to indentation is important. So these two are 2 different code blocks, but they're indented at the same level. You can also have chained else if here. So you can if I equals to 0, do this. Otherwise, if it's less than 1, do this. Else if it's greater than 1, do this, and so on. And then finally, you can have a final else clause here, somewhere in between, like this. And you can also have nested statements here. So, for example, this entire code block is if I not equal to 0, it will execute this entire code block, which is in turn has its own if statements here. But I think it's still you get the structure really quickly by just looking at it. And that is one of the goals of Python, also to be very, very readable. But you need to make sure that you have the same indentation everywhere. So how do you control iterations? So there are two ways of doing it. There is a break statement, which exits the loop. Yeah. And we have continue, that continues to the next iteration. So in this case here, I have a loop that goes from 0 to 19. And if it's 10, prints out exit and do break. So this will jump out to this part here. Then I have, if I equals to 5, go to the next iteration, I use continue. That continues to the next iteration. You can see here, I equals to 5, go to the next iteration, continues here to 6. It comes to 10, and exits the loop, so it never goes to 19. I think you should be a bit careful with using this too much, because it makes the code a bit hard to follow. Because you kind of, sometimes you break and sometimes you continue, and most of the times you don't have to use any of these. You can just exit the loop anyway. But it's good to know that you can do this. So let's do let's see here. I show the answer here, but we can try here and copy this here and see if we can find where the code, there is some error here. So if we start running this one here, so what is the problem with this code here? So if we start here, is that it's unexpected indent. And you can see here that we have the space too much here. So let's move that. And we run again. Now it complains expected a colon, because we have a for statement here that doesn't end with a colon. So that's the second error. So you can actually, you get a lot of information. It actually even points to the where it's wrong here. Now, the parenthesis was never closed. Yeah, because we have a print statement here that doesn't have an end parenthesis. This thing here with n equals to, it's a special form of print. So normally when you do a print statement, it always does a line break, go to the next line. We can control what it should do at the end. So end here says that instead of doing a new line, do a comma. That means that if we iterate here, it will continue printing out on the same line. And then print here will do a new line. So you can see here that first it prints I here, then it goes from J to 0 to 19, and prints every number after each other. Then I have a print statement that goes to the next line. So we should do a for loop that should iterate over the values in the following list. And so let's try here. We have to first define our list, so we copy this over. And now we have to loop. Now we can do it multiple ways. If we just want to have print out the values in the list, we can do for value in L, print L. We should print the value. I print at least several times, like that. We can also do, another way is to do for I in range, then L. like this. Gives the same thing. We can also do I, b in enumerate. I think it was that. Let's check. Yes. But then we can just use I, b here instead, because we get the value directly here from the list. But now we can print out I instead. So that is how you can list over a loop. So next building block we need in Python is the ability to group code, or group code together in functions that you can reuse in different ways. And functions are defined using def keyword. And then you have the function name and the parentheses that with any parameters if you have any. And then you see here colon again. That is code block. Next line indented. So every function body the block for the function needs to be indented one step to the right. So if you execute this code, nothing happens. The only thing we did now was to make sure that this function exists in our current context. But now we can call the function just like this. And now you see here it printed out what it executed this block of code in the function. You can have parameters, so you can have a here that is an input variable that needs to be that you can use inside a function. So let's define this function, and then we call the function with a parameter. And also, even if you say a here, you can call the function with any variable. It doesn't have to be named a. You can call it with b here, but inside the function, b will be a. Like this. Then you will think, what happens if I change the value of a in my function? Will it affect the variable outside or not? Certain languages it will do that, but we will see what happens here. So let's define this function here. And then we have a here is 42. We print value and pass a over to the function, and then we print a again. It didn't change. But what happens here, a equals 42, that is a reference to variable outside here. We pass it over here. We print out a here. When we do this, we create a local variable in the function, which will assign 84. This is not the same variable as this one here. It's a local variable. So you can't pass or change function outside a function by assigning a variable inside a function. So after this function has been called, a is gone again, the local a. The global a here is still there, and you can see here it's still 42. You can modify things inside a function. So in this case we have a here that is a list instead, and we modify a here. We pass the list over and modify a0 here. And this actually modifies the list. Because the list a here references a list in memory. We pass that over here. The a represents a reference to this list. And if you change the value inside the list, this outside list will be affected as well. So that you can do. So passing list over the function and working with those lists modifies the values even outside the function. If you want to just return values from a function, you use the return statement. In this case, we define a function here. We use return here to return the value of sinus x here. So for this to work, we have imported all the functions in the math module into our current context, so that will work. You can also return multiple values using return x comma and x divided by 2. Then you also need to catch two variables at the same time. So in this case here, I assign x equals to pi divided by 2, and then I call the function f here with the x printed out. And if you have two return values, you need to do x comma y and call the function like this. So that prints out two values. This one I already did, so I can remember why this is there. So now we have a small task here again. So we need to implement this function here, 2x raised to 2, 2x plus 3. So what we do then is we start with using the def function here, f of x. So we need to have the variable that goes into the function. Now we indent, it's smarter than me here. Return, and then we do 2 times x times x. You can do that, but you can also do x times 2 like this, plus 2 times x plus 3. And then you can call this function here like this. So this is raised to, so the same thing you're doing x by times x. So def, you define your own functions. Start with a colon, then you add a code block that with all the statement that contain that is going to be inside a function. Yep.
Isn't it possible to do the x and then like the little arrow up to?
Not in Python, I think. Let's see, x. I think that, yeah. You can see this is not an operator for float and integers.
So 2 stars is the same?
Yes, yeah. This is something that is one of the things that changes between the languages.
Yeah.
Yeah. So another thing that when your program is growing, now you start your code and you save your files into a single Py file. This is your source code, and you execute your code. When your program gets larger, you don't want to have everything in a single source code file. So in Python, you can organize your code into modules, and you have already been using modules when you import certain things. For example, you can import the math routines, for example. That is a module, and it's super easy to do modules in Python. I'll come to that, but this is import that will import a module. And this form, you have to prefix every call with the module name and then the function like this. If you don't want to do that, you want to use the functions directly from this module, you use the from statement. So from math import star. That will make all the functions in math available in your current context. So in this case, you can type print sin pi divided by 2. This is a bit frowned upon because there are actually libraries that define a function with the same names. And if you do this import, it's the last import that is the final say. So you can do multiple imports, and then we overwrite the functions here. So for example, NumPy also defines the sinus function. So if you do from math import star, from NumPy import star, you will get a clash. You will not get the math version of it, unless you change the order of import. But sometimes it makes the code more readable if you do it like this. You can also just selectively import certain things. So from math import Siemens square root. Another way of doing it, you can also do from math import. I will go into that later, but there are multiple versions of doing this. But the thing I want to come to here is that all source files in Python can be used as modules. So if you have a source code file in your directory, you can import that into another source code file, and that will be treated as a module. So you can create function library by providing functions into source code files, and you can use them in your main code or something to import, just like you do with other modules in Python. So for example, here I have this is my source code here, and I have it uses the square root function here of math. I define a function called isPrime, does some things here, and returns true or false if it's a prime or not. Because it's a bit difficult to test here, so I will actually get the file here and put it in the notebook directory here. So if you look here in the folder here, I have a file called prime.py. And what I can now do is I can do this, import prime. So basically look for that file in your source code directory and import that into my current context with the prime prefix. So what I now can do is I can call this function from that function with a module. And the entire call fem for Python is implemented this way. So there is a call fem.core, which is actually a core.py file containing all the element routines, and we import them. But they're basically just source code files in Python. Like this. So when you will in your worksheets here, when you build a program, you will use modules. One module for your finite element model, one module for the user interface, and so on, to kind of structure your code in a logical way. So main programs and scripts in Python. So because Python is a scripting language, it reads a file, executes every line. But sometimes you want to differentiate between being a module and being a main program. You said here you can use you can use import to import a module, but that could also include executable statements. So sometimes you need to determine if a program is imported or source code is imported or run as a main script file. So for example here, I have a special version of my prime called prime extra here, and you can see I print something that's called name. When you have these underscores in variables in Python, they mean certain things. So these are reserved. The name here is the name of the module itself. So let's download this. And so when I import this prime main, so this looks like this now, when you do import, it will actually execute statements. So when you do the import, this will actually be printed out. This will not be printed out because it just defines the function, but print will print out something. So let's see what we do. If we run this here, you can see here that it prints prime extra. So the name, this magical variable, returns you the name of the function, or name of the module that's imported. So prime extra here, we will print it here. If I run it from the code, just if you press run in your Python environment, it's not the same thing as importing. And you can simulate that in a notebook by doing the run command here. And now you get something actually interesting here. So now instead of saying that this is a module, the name of this module here, it says main. So when you run a script from the Python using the Python interpreter, it will not be called the name of the module. So import will set the name, running will set main. And this way you can do an if statement in your code to determine if it's run or imported. It's getting complicated, but it's so in this case this will be my main program. I will import prime, and I have if name equals to main. This if statement checks if I'm running it by pressing play in Visual Studio Code or typing Python prime extra. That will be main. But then I know, okay, it's executed as a script. I'm the main. This is the main function of the program. So in this case here, you can see here that it's true because I run it here like this. It executes those two function calls, says false or true. Now I do the same thing with importing the same file, and nothing happens. So by having this here, you can protect yourself from if your main script is imported, this will not be called. If it's run using Python prompt, it will execute those statements. So this is usually when you look at code in, you find Python code online, usually you will see something like this in your main routine. If name equals to main, then the code starts. There is also some people also do it in a slightly different way, that they create a main function, so def main, and then you have if name equals to main called main. So that is also a construct you can see. I wanted you to see this. So there's nothing preventing you from having a main program without this construct. You can just put your executable statement in a certain file and run that file. It's just when you don't want to mistakenly execute code when you import something. You can use this clause here, this protection clause like this. Okay, I think we'll do a break here, and then after the break I will continue with how to print nicely. So next we will go through how to print data in a better way. And some of you have already started with some of the worksheet exercises, and printing floating point will print in the highest, you get all the decimal places, and sometimes you don't want that. So formatting output data, from Python is really good at that, and we are going to look at using the .format method that is part of a string method, and it's basically like you kind of create a template for how you want to print it output to be. So in this case here I have 4 variables of different types, these, and the first thing you do is you create a string that is your template. So I want to have 4 numbers here, or 4 outputs with a comma and a space separated, and each of the values is contained in a curly bracket. So the first value goes in the first pair, second pair, third, and so on. So the format here you put directly on the string, and then you just pass the variables over, and they will be placed in the string. Looks like this. So if you want to have less space between, you can do like this, and you can see here it changes. You can also change the ordering. So if you put numbers in these curly brackets, you can change the order of the values in the output. So that's one thing. Next, we want to also be able to specify, for example, strings. If you want to do column output, you want to have a fixed number of characters for each column. You can do that by specifying a colon and 15 here. That means that the field size will be 15 characters. And these larger than and less than here, I just put them there to kind of indicate how long the string is. It's difficult to see otherwise. So if I run this here, you can see I have Python 3 here, and I have 15 characters here. So the field width is 15. You can also see that it left justifies the text, so it will on the left side. But you can actually specify if you want it to go on the other side. You can have a character here that is, so that says that it should go on the right side. It points to the direction it should be formatted to. So in this case now it goes on the right side of the column here. And you can center by using the @ operator. So it can be used here, but not in math. And then it will center the string inside the column width like this. You can also tell Python that I want to have the spaces should not be spaces, but an underscore, for example. So then I can put here the underscore character here, and then it should be centered and 15 wide. Then you got something like this. So it fills the empty space with underscore characters. So that is the way you format strings. Integers, you can do the same thing here. You have D here. I want to have there's an integer variable coming in here. You have a D. And then you can do, it prints out the 42 like this. You can do the same thing for integers. You can do 10 here for the field width. And you can center it and you can move it around in different ways like this. So it's basically just like the strings here. And also the final one here you can have, if you want to have a number that is 001 and 002, and so you can specify the filler here to be zeros here. Floating points. Here you have a bit more options. So you have here 10 here is the field width, and 2 is the number of decimal places. And the F placeholder is it's a fixed notation, so you don't have it will don't go into scientific notation in this case. So if I print it out, you can see here the differences here. 3.14, that is 2 decimals. 4 decimals, 10.4. And 6 decimals like this. You can also use scientific notation, and then you use, instead of the F here, you use E, and then it will always print scientific notation. If you have J, it will select a suitable notation. So here you can see that it always prints out scientific notation. Here it will select, depending on the field width and so on, if it should use it or not. Another cool thing is that you can actually have named placeholders. So this here you can have X and Y, and then in the format statement you can have X and Y here as well. So you can map them to a certain... Oh. I'll remove this one. You can also use dictionaries with values. And then you can just pass along the dictionary directly to the formatting string here, like this. And then you have to use this notation here. You have to have double star in the beginning here to put it to pass it over to the string format string. But the cool thing with this is that you can, in Python, everything actually in Python is dictionaries. So there is a special globals function that will return all the variables in your global scope. And that is actually a dictionary. So what you can do is, if you have values like this in your code, you can just pass this variable into the format statement. It will replace all the values with the correct ones and reference the variables outside here. And that comes to the coolest feature of Python now is the F strings. So the formatting is kind of how it's implemented. There is a method called .format here. But what they added in later versions of Python is that you can, by specifying a prefix to the string with an F, it basically behaves like this statement here. So instead of having to specify the global statement, you can actually just do printf value 1, value 2, value 3. And then you can do value, and then you can specify the specific the field width and the filler and so on directly in this. So you can, in your string, you can directly refer to variables outside the thing here. So you can see here that you can use the same notation for floating points inside every placeholder. And this is really simple if you want to do nicely formatted output. You don't have to think too much. You just have to remember the curly brackets and put an F in front of the string. Really nice way to use to do formatting easily. Next is something that almost all programs need to do. Your program will read the input parameters of your model from a file, and then also be able to save those to a file. And to be able to do that, you have to make a connection in Python from a file on your disk in a folder somewhere to an object where you can so that you can read and write to that file object. And you create the file object by using the open statement. So it's I open the file and I get the object back that I can manipulate. So just doing this, we'll open a file, and there are two parameters. The first one is the file name. The second one is what you want to do with the file. In this case, I want to write to this file. So I put a string here with a W for write. Run this, nothing happens, but I get back a text file object. So using this text file object, I can now write to this file. And there are some methods to this object. And the important one is write. That will write to the file. It does not work like the print statement. It doesn't do a new line every time you call it. So this will write to the file, and there is a invisible cursor in the file. So if you could call another write statement, it will continue writing after that invisible cursor. If you put a backslash again, there will be a new line. And then you need this one here. So if I execute this, still nothing happens. And when I'm done with writing to my file, I need to tell the operating system, Windows or Linux or Mac, I'm done writing, because modern operating systems, they try to avoid writing directly to disk. They kind of cache it in memory to make the disk access more efficient. So until you basically close the file, it can be in memory. So when you call close on the file, it will actually write the file to disk. And we can see that now here in our folder. I have a myfile.txt here. And if I open that, so you can see here that the contents of this file is a text file. You can see here that I wrote the first part here, and then in the same row, then have a new line here, and then there's new text here. And I can show it like this. If I want to go the other way around, I want to read it back from disk, I can do I do the same thing. I need to create a file object. Still use open, but instead of using W, I use R for read. And now there are multiple ways of reading a file in Python. Of course, you can do, in Python always have many ways of doing things. One really quick way is just call the read method. That will read the entire file into a string and return it back here. If we have files of gigabytes of size, it's not recommending to do this because it will load that into memory and it could blow up. So for smaller things, fine. I still need to use close. And then if we do print content, you can see that this is a string now containing the files I wrote to disk. You can also use iterate when you open a file. So here I open the file, I read a single line, and as long as the line is not empty, I continue reading a line from the file, and then finally I close it. And you can see here the read also reads the new line character. So the thing is, what the problem here is the print. You can see the spaces between here. That is because print will read this contains a new line, and print will add a new line. That's why I have double spaces here. So to solve that, we can do rstrip on the string. That will remove any trailing characters, and now it will print every line like this. So when you come to the end of the file, this line will be an empty string. So in this case here, you can continue reading until that's empty. But you can do it even more simple. You can use a for loop. You can use, just like you're iterating over a list, you can iterate over a file. So for line in text file. That will read the line, and you can print it out. Read line, print it out. I think this is really an elegant solution. Also, if you need to process a file, sometimes you need to kind of be able to access the file using a list. You can do that as well, and then you can use the read lines method here. That will read the file into a list. So every line is in an item in a list. So if you run this here, you can see here, first line is here, second line is here. And then you can loop that, go back and forth in the file in memory. One thing that you always have to think about is make sure that you call close on the file, because otherwise the operating system believes that the file is open and bad things can happen. So one thing you can do to make sure that you always close a file is that you enclose the call to the open statement using something called with, a with statement. So with open as text file, do the same operation that we did before, and print lines. But what the with statement will do, before it exits this code block, it will always call close on this text file. So you don't have to think about it. So it will, yeah?
What does R indicate in the open context?
I want to read from the file.
Okay.
So you can also have A, which is append, and write to create a new file. So I'm not sure why they didn't have a readable parameter, but they put strings there.
What happens if you don't have anything after? It doesn't read it? Or
Sorry?
if you don't have anything after myfile.txt, it doesn't read at all?
No, you have to call a method on the object.
Okay.
So basically what it happens here is it opens the file, it has an invisible cursor in the file in the first position,
Okay.
and then when you read line, it will read and move the cursor in the file. But this makes sure that you always close the file. So finally here, we will look a bit about when you're working with files, you have to think a bit in depth. So it could be that the user gives you a file name that doesn't exist. So in that way, you need to make sure that you check before you do things that certain things can be read. So one thing you can do is you can use a logical way approach to this. So I import a module called OS, which is operating system, and that contains a lot of good functions to check for things. So in this case, you can do OS path exists. So you can check here, does this file name actually exist? And when you run this, it will Python script started will always run in the directory it's located. So if you don't specify any paths here, it will look in the same folder. In this case, if it's true, then it opens the file and reads. Otherwise, the file couldn't be found. So this is one way of doing error handling in Python. Nothing wrong with it. It's just that you make all the things to yourself. You have to think about all the things that can happen. Another way you can do it is using exceptions. And you have already seen the exceptions. When I did some error in the code, you get this red statement on the thing, and there was a name or something, index error or something. That is an exception. And you can actually test for this. So if you run this code here now, you see here, file not found error. This is the exception name. And this is an error statement, and that will stop the program if it's not handled. But you can actually handle the exceptions. And what you do then is that you use something called a try except statement. Or it's a combination of try and except. So try, then you have a code block so that you expect an error to happen. And if anything happens, print out this. This is bad code, but I will come back to why it's bad. You see, the file couldn't be opened. But in this case here, it will actually catch every exception. So you will never know what actually happened. It could be that you didn't have permission to actually access a file. Then the error is wrong here. So this is kind of a blanket catch-all error handling, but you don't know what actually happened. So if you want to handle specific exceptions, you need to give some hints on what kind of exceptions you have. In this case here we have, you saw before when we ran it, you got this file not found error. So that's an exception we can catch. So we can actually specify here, try file not found error. So this will only catch this specific exception. And then now, okay, the file was not found. And then you can list more. File not found, permission error, value errors. So depending, you can actually, one thing you can do is you can run your code without the exception here, and then you can just see what happens, and then you just catch the specific errors that you want to catch. So in this case, there could be that you don't have permission, so then we can say, vi har inte rätt att läsa fil. Couldn't convert to float. Value error is something you will probably see in your finite element code, where you need to, when you create a user interface, all the user interface control returns strings, and you need to convert those strings to floating point values. And if the user is kind of doesn't know what to do, he puts an A in a text box, and you press calculate. It takes the A and tries to convert it to floating point. You get an exception. So you need to kind of, and then you can handle that error. So, oh, you have something wrong in your in the text box there, and please fix that before you do actually run the code. You can also, if you want some more information about the exception, you can actually catch it as an object. And then you do file not found error as E. And this E is the actual exception object, and you can query that. So for example, the file not found exception has a property called file name. So you can actually see which file name had a problem. So could be I have a long code here and you just don't know exactly what file it was, you can print it out. Usually this will be a variable in your code, so you perhaps want to show the user that this file name couldn't be found. There's also another way. So suppose you have an error and you need to terminate the program, but you want to kind of make sure that everything is closed and cleaned up in a certain way. You can have another clause here called finally. So if you have an error, you will be guaranteed that this will always be done, regardless if you have an error or not. So yeah, so you get a lot of errors here, but this is always called. So it went here and it performed those actions. So that is yeah. So this was a basic Python introduction, and I will start going through the NumPy part as well. So up until now, I went through all the standard Python things, and we've gone through the data types that are built into Python. But when it comes to arrays and matrices and stuff like that, lists and dictionaries are not the data type to use because they are not contiguous in memory, and also they are really inefficient to do computations. And NumPy is an extension module that is not part of Python from the beginning. You add that to your Python. If you install CondaForge, when you install the software for this course, you added NumPy and SciPy. Those are scientific libraries for computing arrays and matrices and stuff like that. And the extension handles large arrays of the same data type. So in this case here, you need to define the data type for all the elements in the array when you create it. So you can't change the data type when it has been created. And that also, but because of doing this, it's really efficient in memory of your computer. The computer can do really fast calculation because it knows that this is a contiguous block of the same data type. So how do you use NumPy? So the first thing is that you import it in a certain way. And the reason for that is that you don't want to have name clashes with other functions in Python. So you import NumPy like this. Import NumPy as NP. And when you do that, instead of having to write NumPy in front of every function, you write NP instead. And this is kind of an established way of importing NumPy. So you will see this in many codes that you do this. So if you want to call the sin function of NumPy, you do np.sin. So it doesn't clash with the math library in Python. You can use it without any risk. The most important object in NumPy is the array object. There is a function called np.array that can create array objects for us. So in this case, I do np, or a equals np array. And the second parameter here is optional, and it's the data type you want to specify. So all the values in this array will be floating point. Even if I specify integers in the array, it will be a floating point array. And if you print an array, I forgot to import NumPy. Like that. You can see that it's floating point array by adding a dot after its value inside the array. If you don't specify a data type, it will kind of guess what data type it is and assign the data type specifically from what the data type is in the list here. So integers here, it will produce an integer array. Also, if you have floating point values in your array here, it will also be a floating point array. And as I said before, you can only have the same type, so you can't have a string in the middle of an array. So if you have created an array, it will have the same data type in the entire array. You can create multi-dimensional arrays, and then you just have a nested list. This is the first row, second row. First row, second row. And you can see when you print them out, they know about their shape. So it's very similar to the arrays you create in MATLAB. They know their shape themselves. And if you print them out, it will print it out in the number of rows and columns that they contain. One thing to know is that when you allocate arrays in memory in your computer, it's not allocated in the shape that you create them in for yourself. So if a 2x2 array or 4x4, it's never stored like a 4x4 array in memory. It's always stored like a linear one-dimensional array. So for example, if I have an array A here that is shaped, it has 6 rows and 5 columns, it's actually stored row-wise. So you can see here how, if you look at the array, it stores them like this in memory. So it goes first row, second row, third row, and the storage of memory is like this. It's just a linear line. So what NumPy does is it creates an abstraction for you to work with arrays. But for the computer itself, just have okay, here is a ton of floating point values, and you interpret the array in a certain way. And what it actually does is that you know to go to second row you have to skip a certain number of items here to go to the next row. But you don't have to think. You have to. I think it's good to have that in memory. That it's like this. And when you're working with NumPy, you don't have to think about it too much because the array itself knows its shape and can handle the access to the elements. And you can query information about arrays in different ways. So A, B, C, with different shapes here. So you can see you have a one-dimensional array, two-dimensional, and here is actually a three-dimensional array here as well with multiple layers. And there is an attribute called shape that you can query to see the actual shape. You can see here that you have 4 here. So 4 elements. The second one is 2 by 2, and the third one is 2 by 2 by 4. And the way you can use this is that you can very quickly get the number of rows and columns by doing this assignment here. R, C equals B dot shape. You can also query the number of dimensions for an object, an array object, using the ndim attribute. 2. And I just did an example here of different attributes here. So in this case, you can see here that the shape is 2 by 2, number of dimensions are 2, and the data type here is the actual store data type. And int here means integers. 64 is the number of bits. So it's 64-bit integer. And if you divide that by 8, it's a 4-byte integer. No, sorry, it's a 4 by 4. An 8-byte integer. So array size, so item size is 8. So every it's 8 bytes, and the array size is 4. So size is the total number of elements. So here are some those are kind of good to know. So using this one, you can actually check the data type of the array, and if it's floating points, it will say float 64. This is just you can ignore this line. Only important thing, the memory of here will return the memory location of an array. So I will use that to kind of see that you can actually reshape an array without actually reallocating or copying any elements. So NumPy is very good at avoiding copying data. So because if you have large arrays, the thing you don't want to do when you are doing computing is recreating an array again. So it works to great effort to kind of try to reuse existing memory. So here I have A is a 2 by 2 array. And then I reshape this to a flat array here using the reshape method. So I create an A flat, which is a new array, and it's based on A, and it should be 4 by 1. So 4 rows and 1 column. And then I print it out here, and then I check the memory of that one as well. So you can see here I have 2 by 2. Memory location in the computer is this value here, somewhere in memory. Reshaped version of it, same memory location. So this is something you have to have in mind when you're working with NumPy. If you reshape things, it's another view of the existing memory. So for example, if I change a value in A, it will also affect the reshaped version of it. "42 here, 42 there." So it's different views of the same memory. If I don't want that, I will use the same thing I used yesterday. You can use a copy. So C here is a copy of A. I changed C00 to 84, and I will check how the memory location looks like. So this one here, we can see here that this is one memory location, this is a different memory location. So with copy, you can change this. You can make sure that you have a copy of the data and not a view of the data. But they have done this to kind of prevent you from shooting yourself in the foot sometimes, because you can imagine arrays can be gigabytes in size, and if you start doing copying, it will take a lot of compute time, and you don't want that. So that's why by default NumPy always does views of the data if it can. Reuses memory as much as possible as well. Yeah, here is some other reshape here. This is not the same thing as doing transpose of data, for example. So you have to make, reshape will just kind of put another view, same data, but it's not a matrix transpose. So that's why these are different here. This is not the same as this one here. Then if you want to resize, or you can use the resize method instead. That will reallocate the array again. If I 2 by 2 here and I resize the base here to 9 by 9, it will reuse the data inside. So you can see here that 1, 2, 3, 4, but it will repeat the data in the resized array as well. But it will be a costly operation. It will need to allocate more data for the new array, but it will copy the data over. So there is some cost involved in these operations. So creating arrays like we have done up until now is not really efficient if you have really large arrays. You can't put them in source code. You need to be able to create them on the fly and read data into them somehow. So if you want to create arrays with a certain size, you can do that using the zeros method. That will create a 5 by 5 array filled with zeros. The same thing here, you can add a second parameter here, which is a data type. So by default, it will actually create a floating point. So if you want an integer, you need to specify int here. And then there's also a similar function for creating arrays that have ones instead. And ones is actually very good to, if you want to create a fill array of values, you can use. I will come back to that. This is one array, and then you multiply with 42. If you multiply an array object with a scalar, it will actually multiply all the values inside the array with 42. So in this case you get an array with fill of 42s. Just like the normal list, you can create ranges of values, and the function to do that is using the a range, so array range, and it works just like the range command when you use the for loops. It creates values from 0 to 9, like this. But now it's actually a NumPy array. It's not a list. It's a NumPy array. And in this way, using this, you can create, for example, a 10 by 10 array going from 0 to 99. So you can do mp.reshape a range 100 10 by 10. First, you create a long array, one-dimensional 0 to 99 values, and then you reshape it to 10 by 10, and then you get something like this. And just like with the range, you can do a start and end. So start -10 going to 10, and here you can set the floating point, and here you can have a step length as well. You can also create identity arrays, so an array with ones in the diagonal using the identity function. You can see you have ones in the diagonal. And one thing that, so you can use a range to create ranges of floating point values. But if you want to have an array with a linear variation, you shouldn't use the arange function. You should use something called linspace instead. So with linspace, you can create a range going from 0 in this case to 1, and then you can specify the number of values you want, and it will interpolate here. So in this case, I want 10, the array to be 10 elements, and it will do a linear interpolation of that. So you can see here I get 0 to 10 here, that one, and you can change 20, you get more. It will interpolate between those, so from 0 to 1, but you can have as many values as you want. So if you're going to do some plotting later, you can do an X array from 0 to pi, for example, and then you have 1,000 elements, y equals to np.sin x, for example. So now we're coming into MATLAB territory. So you can using arrays, you can actually do expressions with arrays. So let's do this one here. So I have a 5 by 5 array here. If I add a value to this, it will add the value to all elements of this array. Same thing here with multiplication. Multiply all values by 3. You can also use functions that are built into NumPy. So you can compute np.sin a, that will compute sin a of all the values in the array. You can do minus a, then we will negate the entire array like this. You can add array objects. And actually, these are not matrices, so you can actually add them together even if they are not the same size. And the thing is that it will repeat the elements in the larger array. But then, so how do I do matrix multiplication? So we have a special operator for that. You can either use the a dot and then the array you want to multiply, but you can also use the at operator, which is matrix multiplication. So these two are equivalent. Then you can do slicing. What that means is that you can, just like we did with the list, that you can do start from 3 and go to some part, you can actually extract sub-arrays using certain rows or columns from the array. So accessing elements in an array, you do that just like with this. You access the element like this. If you want to have a two-dimensional array, you do square bracket, rows, and columns. And here you have the big difference on MATLAB. The arrays are zero-based. So you don't have the first row is 0, first column is 0. In MATLAB it's 1. So there's a difference here. If you translate MATLAB code to Python code, you have to be aware that indexing is different. It's zero-based in Python. And the same thing, you can assign values just like with lists. A2 equals 42, 1, 2, 42. Then you can also, just like with lists, you can access them by start and end, start colon, end colon, colon, and so on. So here I can, for example, access the values going from first position to up until not including 5 in this case. So the same rules apply as for the range. So this is it goes from 1, so 1, 2, 3, and 4, but not 5. Also, when you are using indexing or slicing, Python will, or NumPy will try to avoid to reallocate here as well. So you can see here that I have A is a 25 array. Print memory array is 46920 here. I expect B equals to A1 colon 5. I print B, and then I print the memory of B. And you can see here that it actually uses the same memory location. So B, the index, this part here is actually a view of the A matrix, or A array. So B is actually a view into A. So in this case, you need to be careful again. If you change anything in B, it will change in A and so on. So it tries to avoid doing reallocations. Here are some examples of what you can do here. You can, for example, all elements except the last, colon -1, all elements except the last 2, last elements of A, 4 to 9 will set to 2, all elements in the reverse order. And you can do the same thing with two-dimensional arrays. So here I have column, comma 0, all rows in column 0. So you'll probably recognize the same syntax as in MATLAB here when you do indexing. Row 0, row 0 to 1, last row in B, last column in B, every other row, and so on. So it's extremely flexible. Another thing is that when you assign a row in an array, you can use normal list notation. So this right side doesn't have to be an array. So you can just assign a row a list of values. It converts it automatically. So I don't have to do. So the arrays are objects and they contain methods that you can call on them. So in this case, you have sum here, and that will summarize all the elements of an array. You can also just summarize the columns and summarize the rows. You can same thing. You can do product, and then finally here there is a special array type called matrix that has linear algebra operations built in. So you can do stuff like that. A.T, that is a transpose. The multiplication operator for these types are actually matrix multiply, and A.I is the inverse. I will skip this here. You can read as on your own. You can read files here as well. Finally, solving linear equation systems, you can use np-linear.solve A, B. That will solve a system of A equals X, A equals B. That's built in there. For your assignment in CalFrame, you will use the built-in solver in CalFrame that can handle boundary conditions, stuff like that as well. So that was what I wanted to show today.